Welcome back to the deep dive. You know the drill. We take that overwhelming stack of preparation sources, the articles, the leak code guides, the
Yeah.
company-specific pattern videos, and we distill it all down into the concentrated knowledge you need without all the hours of grinding.
Today, we are tackling the true gatekeepers of any technical interview, arrays and strings.
Hmm.
And I mean, no matter what field you're entering, whether it's software engineering, data science, specialized infrastructure, mastery of these is just, well, it's absolutely non-negotiable.
Our mission today is to give you the ultimate revision guide and mental checklist. We've pulled out the common ground, covering the fundamental data structure properties, the core algorithmic patterns like two-pointers, hashing, prefix sums,
Hmm?
and we're linking those patterns directly to the problems you see again and again in interviews.
Yeah, the goal is really to provide that immediate cognitive shortcut. We want you to read a problem and, within seconds, know which tool in your mental toolbox is the right one.
Right. So you see a question and you instantly think, okay, is this about looking up information quickly or counting things?
Exactly. If so, is hash maps or hash sets?
Or is this problem all about indices or boundaries or solving something in place? Then we are definitely talking about a two-pointers approach. That level of systematic intuition is what we're trying to build today.
Precisely. So let's start with the fundamental structure itself, the DNA of the array, before we explore all the ingenious ways engineers have found to optimize problems using that structure.
Sounds good. Let's get into it.
So the core of an array is its physical nature in memory. An array is defined as a contiguous block of memory. This means all of its elements are stored right next to each other with absolutely no gaps. And that physical reality, it dictates everything else.
And crucially, it's also a fixed size data structure. Once you declare an array of, say, 10 integers, that memory block is reserved,
Dang.
and every single slot is guaranteed to hold an integer.
That continuity and that fixed element size is the key to the array's most powerful advantage. Random access and constant time, O1.
O1 is the holy grail of efficiency. But why is it constant time? Can we break down that calculation? I think it's important people really get that.
Absolutely. The computer doesn't need to, walk from index 0 to index 1 to index 2 to find the value at index 100. It knows 3 pieces of information instantly. The starting memory address of the array, the index let's call it I, and the fixed size of each element, let's say 4 bytes for an integer.
So if the array starts at memory location 5000, and I need the element at index 50, and each integer is 4 bytes, the computer just calculates. 5000 plus 50 times 4, which is 5200. It jumps directly to memory location 5200 and pulls the value.
That's it. That calculation start address plus index times element size, it's instantaneous. It doesn't matter if the index is 1 or 1 million. And that is the definition of O1 random access. It's why arrays are fundamental to pretty much everything we do in computing.
But like you said, this fixed, continuous nature comes with some pretty severe trade-offs. What are the two major limitations that array-based solutions tend to run into?
Well, the first is the fixed size. I mean, in dynamic real-world scenarios where data is streaming in or requirements are changing, an array just becomes problematic. If it fills up, you have to allocate a brand new, larger block of memory, copy all the elements over, and then deallocate the old space.
And that's exactly why we have things like array lists,
Yeah.
right? They
Yeah.
handle that resizing pain for us, but it's not free.
Not at all. And the second major drawback, and this is often why we switch to something like a linked list, is the cost of modification. If I have an array of 1,000 items and I want to insert a new element at index 50, every single item from index 50 onward, that's 950 elements, has to physically shift one position down in memory to make room.
Oh, wow.
Yeah, that shifting operation takes time proportional to how much you're shifting. So in the worst case, inserting or deleting at the very beginning, it becomes a linear time complexity operation, O&M. If your app needs frequent insertions or deletions, the array is simply the wrong tool for the job.
Still, despite these limitations, the sources all remind us that arrays are categorized as a linear, non-primitive data structure, and they really are the foundational bedrock. I mean, heaps, which are these specialized trees for getting min or max values quickly, they're usually implemented using arrays.
Stacks, queues, they can also be implemented with arrays, just relying on the speed of that index access.
So that brings us to the first big pattern. When should we immediately think two-pointers?
Okay, so when you see an array problem that requires manipulating the data in place or comparing elements based on their positions or keeping track of 2 separate working boundaries,
Yeah.
your immediate thought should be 2 pointers.
The beauty of this technique is just how efficient it is. You can often get to an ON solution while keeping the space complexity at O1, meaning you don't need any extra data structures like a map or a set.
Let's look at a classic application. Remove duplicates from a sorted array. We use one pointer, let's call it I, the fast pointer, to iterate through every single element, and then we use a second pointer, J, the slow pointer, to track where the next unique element should be placed.
The logic feels pretty simple. If numSci is different from numZ, that means we've found a new distinct value. So we increment the slow pointer J, and then we just copy that unique value from numSci into the new boundary. numsJ equals numSci.
Right. And if they're the same, we just let the fast pointer I keep moving forward, which effectively skips over the duplicate. Since we only move through the array once, it's a clean ON solution.
Okay, another big one is merge two sorted arrays, where you have nums1, which has extra space at the end, and nums2, and you have to merge nums2 into nums1 and keep it sorted.
And here, the key insight is avoiding that shifting problem we just talked about. If you try to merge from the start of nums1, every time you insert something from nums2, you have to shift all of nums1's data. That gets you into ON squared territory really fast.
It's a mess.
Total mess. The efficient solution uses 3 pointers and works backward. From the end, you have one pointer I for the last real element in nums1, a second pointer J for the last element in nums2, and a third pointer K for the very last position in the combined merged array.
So you're always writing into the empty space. You compare nums1I and nums2J, you put the larger of the two into nums1K, and then you just decrement K and whichever other pointer you used. You never overwrite data you still need.
Exactly. We also see this in the Dutch national flag problem, which is a great one for sorting an array with only 0s, 1s, and 2s in a single pass. It uses 3 pointers, low for the boundary of 0s, high for the boundary of 2s, and mid as the scanner.
Right, the scanner mid moves along. If nums mid is a 0, you swap it with num slow and increment both low and mid. If it's a 2, you swap it with numshi and decrement high. But you don't increment mid.
And that's the key part. You don't increment mid because the value you just swapped in from the high position still needs to be checked.
And if it's a 1, it's already in the right spot, relatively speaking, so you just increment mid. That logic just perfectly partitions the array in one single pass. It's beautiful.
It is. Now let's analyze a classic problem that really showcases the power of the narrowing 2 pointers approach. Container with most water.
Ah, yes. You have to find 2 lines in an array of heights that form a container to hold the maximum amount of water. The area is always the minimum of the 2 heights times the distance between them.
The naive approach is ON2 checking every single pair of lines. But with 2 pointers, we start L and R at the absolute edges to maximize the width right from the get-go.
Okay, so you have maximum width, but the area is always limited by the shorter of the 2 walls.
And here is the core logic, the reason the 2-pointer solution is optimal. If we have heights h sub L and h sub R, and let's say h sub L is shorter than h sub R, the current area is limited by h sub L. If we move the taller pointer, R, inward, what happens? The width definitely decreases. The new area will be limited by either h sub L or some new unknown height. But since h sub L is already our bottleneck, moving the taller wall guarantees that the minimum height will either stay the same or get even smaller.
So moving the taller pointer can never possibly give you a bigger area.
Never. But if we move the shorter pointer, L inward, yes, the width still decreases. But by moving the bottleneck, we introduce the only possibility of finding a new, taller height that could potentially offset that loss in width.
I see. So you are justified in completely ignoring all other possibilities from that taller pointer's position.
You are. You prune the search space by always moving the pointer associated with the smaller height. That intelligent move turns what looks like a geometry problem into a super efficient ON linear scan.
All right, so moving from problems that are all about index and location to problems that are defined by content like frequency, repetition, or quick lookups, we enter the realm of hashing.
Yes, and this is where hash sets and hash maps become your best friends because their core operations, search, insert, remove, are all expected to be O1 time complexity.
The move to hashing is almost always about avoiding a bottleneck where you have to search the array over and over. And the perfect example is the two-sum problem.
The one everyone gets asked. Given an array and a target, find 2 numbers that add up to it. The brute force, as we've said, is ON2.
And a lot of people's first clever step is to sort the array, which gets you to ON log n if you use 2 pointers after that.
Which is a respectable improvement, but it's not the best. And interviewers want the best.
So why isn't ON log n good enough here? Doesn't the interviewer prefer a solution that uses less memory? The hash map takes up extra space.
That's a great question, and it gets to the heart of complexity trade-offs. While O(n) log n is good, the goal is always the most optimal time complexity, which the hash map gives us at O(n). We willingly trade O(n) extra space for that gain in speed. In almost every competitive context, O(n) time beats O(n) log n time, even if it costs a bit more memory.
Okay, let's unpack the ON hash map solution for twosome.
So we use a hash map to store the elements we've already seen along with their indices. So the map stores number index pairs. As we iterate through the array just once, for each element num_sci, we calculate the complement we need. Need is target num_sci.
And instead of scanning the rest of the array for need, you just ask the map, do you have this key?
Exactly. That lookup is O(1). We immediately know if a solution exists. If it does, we return the stored index and the current index I. If it doesn't, we add the current pair num_sci I to the map and just move on. A single pass, n lookups, n insertions, all O(1) ops, which gives us a total time of O(n).
Hashing also makes quick work of duplicate problems. Like, contains duplicate is just iterating and trying to add everything to a hash set. If the add operation ever fails, you've found your duplicate, O(n).
And this is where patterns start to combine. Contains duplicate 2 asks you to find a duplicate, but only within a specific distance k. This merges hashing with the sliding window technique.
Ah, okay. So you use a hash set, but you have to make sure it only ever contains elements from the current window.
Precisely. For each element num_sci, you first check, is this element already in my set? If yes, you're done. You found a duplicate within distance k.
If no, you add num_sci to the set. But before you move to the next element, you have to maintain the window size. This is the critical step. You have to look back at the element that just fell outside the window, the one at index ik, and you remove that element from the hash set.
And by using O(1), insertion, lookup, and removal in the hash set, coupled with a single O(n) pass, the whole thing stays incredibly efficient.
And finally, of course, hashing is the basis for basic frequency counting. Using a map to store element count is the starting point for almost all counting problems, like finding the top k frequent elements.
Now, when the problems shift from individual elements to the properties of a contiguous subsection of the array, like finding a maximum sum, we need to think about accumulation and prefix-based patterns.
And the king of this category is the maximum subarray sum problem, which is solved by Kadane's algorithm. The challenge is finding the continuous subarray, which can have negative numbers, that gives you the largest possible sum.
Kadane's is famous because it takes what feels like an O(n)2 brute force problem and just slices it down to O(n) with a really clever local perspective.
Right. The core of the algorithm is this decision you make at every single step. As you scan the array, what are the two choices you face for the current element, num_sci?
The choice is simple. Do I, 1, discard everything I've summed up so far and start a new subarray, beginning with just num_sci? Or 2, do I extend the existing subarray by adding num_sci to my current running sum?
And to do that, you maintain a local maximum. Let's call it max ending here. This variable tracks the best possible sum that must end at the current index I. The logic is just max ending here, math.max num_sci, max ending here plus num_sci.
Exactly. And then, totally separate from that, you have a global variable, max_so_far, which just keeps track of the absolute biggest sum you've seen anywhere in the array so far, and you just update it with max_so_far x_least.max. Max_so_far, max ending here.
Let's walk through an example to make that super clear for everyone. Let's use the array. Max2, 1, -3, 4, max 1, 2, 1, -5, 4.
Perfect. We start max ending here and max_so_far are both max_so_far. Next is 1. Do we start new with 1 or extend with -2 plus 1? We start new. Max ending here becomes 1. Max_so_far updates to 1. Next is -3. Do we start with -3 or extend with 1 plus 1 is 3? We extend to -2. Max ending here is -2. Max ending here stays 1.
Okay, I'm with you. Now comes the 4.
Right. Do we start fresh with 4 or extend with -2 plus 4? 4 is better than 2, so we start a new subarray. Max ending here becomes 4. Max_so_far updates to 4.
And you just keep going like that. The next few values extend it. 3, then 5, then 6. Max_so_far gets updated to 6.
Right, and it just continues to the end. The final answer is 6, found efficiently in one pass. It's amazing how much complexity that one mac.max line really handles.
It really is.
Yeah. Okay.
Okay, so moving from sums to products, we get to product of array except self. This is a great one, where you have to calculate the product of everything in the array except the element at the current index, and you can't use division.
The key realization here is that for any index I, the product you need is just two things multiplied together. The product of all numbers to its left, the prefix, and a product of all numbers to its right, the suffix.
And you can get this with a clever two-pass approach.
Exactly. O(n) time and O(1) extra space, because the result array doesn't count. First pass is left to right. You keep a running product. At each index I, you store the current running product before you include nums_i. So resi gets the prefix. Then you update your running product.
And the second pass is the same thing, but backward, right to left. You keep a running suffix product. At each index I, you multiply what's already in resi, the prefix, by the current running suffix product. Then you update the suffix product.
And after that second pass, the result array has exactly what you need. It's a superb example of breaking a complex problem into two clean, linear scans.
Okay, now for what feels like the ultimate combination of these ideas. Subarray sum equals k.
Ah, yes, a common and tricky one. You need to find the count of all continuous subarrays that sum exactly to a target k. The naive ON2 solution is just checking every possible subarray.
But the optimal ON solution uses both prefix sums and hashing.
That's right. The logic is based on a simple math trick. If pi is the prefix sum from index 0 up to I, then the sum of any subarray from j to I is just pi minus pj1.
We're looking for a subarray that sums to k. So we're looking for some previous index j1 where pi, pj1, plk, k.
And if you just rearrange that equation, you get pj1, pj1.
So as we're calculating our running prefix sum, pi, at the current index, we don't need to look back through the array. We just calculate the target prefix sum we need, pik.
Exactly. And we use a hash map to store prefix sum count. For every current running sum pi, we check the map for the key pik. If that key exists, the count associated with it tells us exactly how many subarrays we've just completed that sum to k. We add that count to our result, and then we update the map with the current prefix sum. It turns a quadratic search into a linear lookup.
Okay, so not every array problem is a linear scan. When the data has structure, like being sorted, we should be thinking logarithmically. We should be thinking binary search.
For sure. And the classic modification problem is search in rotated sorted array. The array is sorted, but then it's been shifted by some unknown amount. You still need to find a target in O log n time.
Standard binary search breaks here because the middle element doesn't tell you which way to go reliably. The trick is figuring out which segment of the array is still guaranteed to be sorted.
That's the core modification. In every iteration, after you find mid, you have to figure out, is the left half from left to mid sorted, or is the right half from mid to right sorted? You do this by comparing nums left and nums mid.
Right. If nums left is less than or equal to nums mid, the left half is definitely sorted.
Otherwise, the pivot must be in the left half, which means the right half has to be sorted.
And once you know which half is sorted, you can check if your target could possibly be in that range. If it is, you search there. If it isn't, you know it must be in the other, unsorted half.
And you just keep repeating that by always using the sorted property of at least one half to cut the search space by 50%. You maintain that critical O log n time complexity.
Finally, let's touch on those cool math shortcuts that save you from using any extra memory.
Right. These are great. The missing number problem, where you have an array from 0 to n with one number missing, is a perfect example.
You just use the sum formula, right? The expected sum of numbers from 0 to n is nn plus 1, 2. You calculate the actual sum of the array, and the difference is your missing number, on time O1 space. Super clean.
And the other elegant one is single number, where one number appears once and all others appear twice. The solution is just bitwise XOR.
Because XOR is 0. So when you XOR every single number in the array together, all the pairs just cancel each other out.
And what's left is the unique number that had no partner. It's probably the cleanest ON solution you'll ever write.
Okay, let's switch gears to strings.
Right. So we're now on to strings. And while a string feels like a character array, you get that same O1 access to characters by index, fast length checks. The big architectural difference, especially in languages like Java, is immutability.
Immutability is such a critical concept. It means that once a string object is created, its value cannot be changed. If you try to, say, concatenate two strings, you're not changing the original string. You're creating an entirely new string object in a new memory location.
Which is a design decision with trade-offs. It gives you great security and thread safety, but it can be a performance killer. If you're in a loop building a long string by concatenating over and over, you're creating hundreds of new objects and leaving old ones for the garbage collector.
Which is exactly why we have string builder and string buffer. They are mutable, so you can append and modify them in the same memory location, which is way faster. You only convert to a final immutable string at the very end.
This also brings us to memory management and the string constant pool. This is a special little memory area that the JVM uses to optimize memory for string literals.
So if I write string s1 deep dive and later string S2 deep dive, what's happening?
Only one copy of the actual value deep dive is created in the string constant pool. Both S1 and S2 just point to that same single object. It's a memory saver. But if you use the new keyword string S3 equals new string deep dive, you are forcing the creation of a brand new object on the heap, even if that value is already in the pool.
And that's why comparing strings with versus dot equals is so important to understand. Checks if they point to the same memory location, while equals checks if the content is the same.
Exactly. So despite this immutability, the two-pointers pattern is still the best tool for sequence-based string problems. You just have to convert the string to a mutable character array first.
Simplest application, in-place reversal. Convert to a char, pointer I at the start, j at the end, swap them, move the pointers inward until they meet. ON. Time. Done.
The valid palindrome check adds a nice little twist. You're checking for symmetry, but you have to ignore case and skip any non-alphanumeric characters.
So you still use two pointers, I and j, at the ends, but inside your loop, you have to first advance the pointers until they land on an actual letter or digit.
Right, so you have inner loops. While I is less than j and the character at I is an alphanumeric, just I plus plus I, same for j, but j...
Once they're both unvalid characters, you convert them to lowercase and compare. If they don't match, you return false right away. If they do, you move both pointers inward and repeat.
That logic keeps the solution at ON by efficiently screening out all the jump characters.
Okay, now for the harder one, longest palindromic substring. This one really separates candidates because the simple check doesn't work. You have to find it.
And brute force is terrible, ON3. So we need the expand around center pattern.
The core idea is that every palindrome has a center. So you can just iterate through every index in the string and treat it as a potential center.
And for every index I, you have to check two scenarios. One, an odd length palindrome with the center being the single character at II. Two, an even length palindrome with the center being between two characters starting at I plus 1.
And for each of those, you expand outwards with two pointers, L and R. As long as you're in bounds and the characters match, you keep expanding and track the longest one you found so far.
Since you have n possible centers, and each expansion can take up to ON time, the total complexity is ON2. And for this problem, that's considered the optimal solution.
All right, let's move into some advanced string patterns. What about anagrams?
Just like with arrays, strings benefit massively from hashing when frequency is the key. Anagrams are all about character counts being identical.
The ON log n solution is to sort both strings and check if they're equal, but we want the optimal ON solution.
For strings with just English lowercase letters, the best tool is a fixed-size frequency array of length 26.
Why an array instead of a hash map here?
It's just faster. There are no hashing collisions, no overhead. Calculating an index in an array is one of the fastest operations a computer can do. When your key space is small and known, like 26 letters, an array is almost always better.
So the algorithm is initialize an array of 26 zeros, loop through the first string, and increment the counts. Loop through the second string and decrement the counts.
Then one final loop through the count array. If every single value is 0, they're anagrams. If anything is non-zero, they're not.
And this frequency counting idea is the backbone for the more complex group anagrams problem.
Right. You're given a whole list of strings and have to cluster them. You need a hash map for this, but the question is, what do you use as the key?
The key has to be some kind of unique identifier for that anagram group.
And the easiest way to create that is to just sort the string. Eat, T, and 8 all sort to the key.
So you use a hash map where the key is the sorted string, and the value is a list of all the original strings that map to that key. You iterate through your input list, sort each word to get its key, and then add the original word to the list for that key in the map.
And by the end of one pass, the values in your map are the grouped anagrams. The complexity is dominated by the sorting, so it's about O and K log K, where N is the number of strings and K is their max length.
Okay, last category. Parsing, transformation, and those really complex logic problems that test your attention to detail.
And the absolute prototype for this is the string to integer, a toy function. It seems so simple, but the edge cases and overflow handling are where everyone messes up.
The solution has to be a disciplined 4-phase linear scan. What are the phases?
1, skip any leading white space. 2, read an optional plus or sign. 3, read the digits, and this is the hard part, check for overflow as you go. And 4, return the final result with the correct sign.
Let's focus on step 3, the overflow check. This is where people fail.
Mhm.
You have to check for impending overflow before you do the multiplication that causes it.
Right. Integer.mx value is about 2.147 billion. So before you do result 10 plus digit, you have to check. Is my current result already greater than integer.x value 10?
If it is, multiplying by 10 will definitely overflow.
And there's a second, more subtle check. What if result is exactly equal to integer.mx value 10? Then it depends on the next digit. If that digit is greater than 7, adding it will push you over the edge.
So it's a two-part check that you have to do in every single iteration of that loop. It's really tricky.
It is, but it keeps the whole thing ON.
Okay, moving from parsing to validation. The classic problem that requires order maintenance is valid parentheses.
And as we touched on, a simple counter doesn't work because is invalid order matters. The closing bracket has to match the most recently opened one.
Which screams stack.
Absolutely. The optimal solution uses a stack for the opening brackets and a hash map to quickly map a closing bracket to its required opening partner.
So as you scan, if you see an opening bracket, you push it onto the stack.
If you see a closing bracket, you first check if the stack is empty. If it is, that's an invalid string. If it's not empty, you pop the top element and check if it's the correct opener for the closing bracket you're looking at. If it's a mismatch, invalid.
And the final crucial check is at the very end. After you've traversed the whole string, is the stack empty? If it's not, you have unclosed brackets. Only an empty stack at the end means it's a valid string.
Exactly. And finally, let's just touch on one of the most involved string problems. Text justification. This is a major test of handling complex conditional logic.
The strategy is greedy. You pack as many words as you can onto a line. The hard part is distributing the spaces to make it fully justified.
Once you know which words are on the line, you calculate how many space slots you have, words minus 1, and how many total spaces you need to add.
And the distribution rules are so specific. First, you divide the total spaces by the slots to get the base number of spaces for each gap.
Then you find the remainder spaces, and those have to be allocated one by one to the slots on the left.
But the whole thing has a giant edge case, the very last line of text.
Yes, the last line, or a line with only one word, must be left justified. That means only single spaces between words, and all the extra space gets shoved onto the end of the line. Mastering that level of multi-rule logic shows real command over string manipulation.
That was a really comprehensive review. We've basically distilled a huge amount of material down into this mental checklist.
Yeah, and just to finalize the takeaways, for arrays, always diagnose the problem type first. Is it about indices and being in place? That's 2 pointers. Is it about frequency or quick lookups? That's hashing. Is it about subarray properties? That's prefix sums or cadanes.
And for strings, 2 pointers for reversal and palindromes, hashing for anagrams. And for anything more complex, it's usually a structured linear scan, often with a string builder or a stack to manage order.
And remember, successful candidates don't just know the answer. They understand why the optimal solution works, explaining the difference between ON2 and ON, and how you got there with pointers or prefix sums or hashing. That's what makes the difference.
Let's end with one final thought, tying back to where we started. We talked a lot about the array's fixed size, but maybe its single greatest limitation. That ON, cost of insertion and deletion, is what drove so much innovation.
It really is. That ON, cost of shifting data, is precisely why engineers invented non-contiguous data structures. By giving up O1, random access, something like a linked list gained the ability to insert or delete in O1 time, assuming you already know where you are.
So the next time you use a dynamic data structure, an array list or a linked list, just think about it. You are benefiting from a structure that was specifically designed to get around the fundamental limitations of the humble array.
The array's weakness truly birthed the entire dynamic data structure family, something to ponder as you internalize these patterns. That was the deep dive. We'll see you next time.